We will continue making elements. Double left click on the start button and then click on the nucleus, and you see here proton. If you double left click proton, and you get one element which we call hydrogen. Hydrogen is an element that has only one proton. And if we add another proton, we get an element called helium. But the moment we have more than one proton in the nucleus, we have to add a neutron. And there are different kinds of helium atoms. Some helium atoms have only one neutron, others have also two neutrons, and we call that helium-4. We call the number of protons the atom number Z. So for helium-4, the atom number 3 is 2. We also know there is a neutron number N, which in this case is also 2 for helium-4. However, for helium-3, the atom number Z is 2, of course, because it's helium, but the neutron number is 1. And if we add the atom number Z and the neutron number N together, we get the mass number A. So mass number A is equal atomic number Z plus neutron number N. The chemist and physicist usually give only the mass number and the atomic number, and then you will have to calculate from that information the neutron number. So for helium-4, this is the mass number. The mass number is down here, that is number 4, and the atomic number is Z. That's all what you get. So here we have helium-4 with a mass number of 4 and atomic number Z. And your job now is to calculate the neutron number. And this is very simple. You put the neutron number over here, and you take the mass number and deduct from the mass number the atomic number Z, and that gives you the neutron number N. For helium-4, the mass number is 4, the atomic number is 2, as you can see here, so the neutron number is also N. The neutron number N is also 2. Let's take number 9, fluorine. The mass number is 19, the atomic number Z is 9. So 19 minus 9 is 10. So the neutron number is N is 10. We understand now what the mass number, the atomic number, and the neutron numbers are. The only number which we have not discussed yet is the number 4.0026, which is the relative atomic mass A with a subscript R. So this is a new vocabulary of physics and chemistry you will have to learn. The relative atomic mass number AR. Here you can see what the relative atomic mass RAM with the symbol AR is. It is the weighted average mass of the isotopes of an element divided by 1/12 of the mass of one carbon-12 atom. And the definition of 1 mu is exactly 1/12 mass of one carbon-12 atom. I think this looks very, very intimidating because you have to know certain things. And here I write the questions down which you have to be able to answer. What is an element? What is an isotope? What is the mass of an isotope? What is the average mass of all isotopes? What is the weighted average mass of all isotopes? So if you can answer these 5 questions, then you know exactly what the numerator is. But then you still have to know what is the mass of one carbon-12 atom and what is the unified atomic mass unit, U or mu. Let's give a very short answer to these questions. What is an element? All atoms of an element have the same number of protons. What is an isotope? All isotopes of an element have the same number Z, but different neutron numbers, number n. What is the mass of an isotope? The mass of an isotope is the amount of matter in its atom measured in kilogram. Here we have two isotopes of copper, copper 63 and copper 65, Cu63, Cu65. Both of them have an atomic number Z of 29, but one has a neutron number of 34 and the other has a neutron number of n equals 36. So it has 2 more neutrons. And the mass numbers differ thereby by 2. A equals 63 and A equals 65. Now, when you look into the atomic mass in kilogram, you will see that Cu63 has 104.492 multiplied by 10 to the power of minus 27 kilogram in mass, while the atomic mass of Cu65 is 107.812 multiplied by 10 to the power of minus 27 kilogram. So what is the average mass of all isotopes? So you have here the 2 isotopes with their masses. So just add these masses together, divide them by 2 because you have 2 isotopes, and the result is 106.152 multiplied by 10 to the power of minus 27 kilogram. This result would be perfect if the isotopes would be 50% Cu63 and 50% Cu65. Then the average mass of a sample of 100 atoms of copper would be 106.152 multiplied by 10 to the power of minus 27 kilogram. However, in nature, we find that copper has a natural abundance that is different from 50% and 50%. So in nature, you find 69% of all the atoms are copper 63, 69%. And 31%, the remaining, are copper 65. So you have to calculate the weighted average mass of all these isotopes. And that means you have to weigh the atomic mass of Cu-63 by 69 and Cu-65 by 31, but divide that 69 and 31 by 100. So here you have the mass of each isotope, and you multiply that mass by the weight, which is the natural abundance divided by 100. So 69% of all atoms in copper in nature are Cu63. And the 69 you divide by 100, and that is 0.69, and that is a weight. And if you multiply now the mass with its weight, you get the weighted mass, which is 72.09948. You do the same for copper 65 with the mass of 107.812 multiplied by 10 to the power of minus 27 kilogram, and the weight is 0.31. That gives you 33.4217. And then you just have to add these two numbers together to get the weighted average mass of copper, which is 105.52120 multiplied by 10 to the power minus 27 kilogram. Wow! So we know now that the weighted average mass of the isotopes of copper is 105.5212 multiplied by 10 to the power of minus 27 kilogram. And we have now to find out what is the mass of 1/12 of one carbon 12 atom. Well, I need to correct an error in the previous presentation. I forgot to write down that the mass of carbon-12 atom of 19.92648 multiplied by 10 to the power of minus 27 has to be divided by 12. So that gives you then the 1 mu, which is equal to 1.66054 multiplied by 10 to the power of minus 27 kilogram. When I wrote that down, I left out the 12.